Okie dokie. So, welcome to June. We only have a couple more weeks left. We're cruising right along. And we, of course, are in the midst of dealing with power series as solutions. So I want to go ahead and open it up first to questions you guys might have. I'm going to guess that we probably want to look at maybe one or two of these. And I'm just going to put this out here first. If you ask me for many of them, I am not doing them all because they are huge. Time sucks, right? So I will get you set up for sure, but I may not go all the way through. So be judicious if you have questions. And yes, I know that this is algebra hell, which is why I'm telling you that I'm not going to go all the way through them before we even start. So, but were there any from the homework that caused you specific issues? No, I don't believe it. Don't you dare say a word, Mikey.
No.
I saw that. I saw that in your face. I was all excited. I was like, sweet. There's not going to be a single question. But go ahead. Ruin my day. I'm like that guy. I'm like that guy who's throwing a perfect game, and it gets to be the ninth inning. He walks out and he's like, "All right, guys, only 3 more outs. Let's do this." And then gives up the home run. So.
Wow. Unfortunately, I'm gonna blame this from being on the road. So, not been probably studying as much as I should.
All right. What do we want to look at?
Obviously, can I look at problem number 1 on 7.3? And I mean, like you said, you can just get me started.
Okay, so from 7.3, number 1, and then Thea, looks like you've got a question.
Yes, number 41 on 7.3.
Okay. I'm just making myself a little note here on the board so I can look at them. All right, let me go find it. Well, first we'll share my screen. And then we'll go find those guys. Oh, wow, I got pretty close. All right, so just good old number 1 here. So it says find the coefficients for at least 7 in a series solution of this. Okay, so we don't necessarily have to go all the way, but we're just looking for the series solution. So let me go ahead and put this up on the board. And I'm not going to worry with the initial conditions just yet, because those are kind of a later stage. So let's go to the whiteboard real fast. All right, so we got the 1 plus 3x times y double prime plus x times y prime plus 2y. Okay, so every time we always start the same way, which is going with a y that's of the form the sum from 0 to infinity, a sub n, x to the n. Now, we might want to use some sort of x minus c to the n. And really what's going to tell us that we want to center it somewhere else? What's the thing that we look for that tells us that?
Our initial starting conditions.
Yeah, you look at the initial conditions if you've got them. Like you pick 0 if you're not given initial conditions. But this one, they told us that our initial conditions are y of 0 equals y prime of 0 equals. So we want to center it at 0. Okay. So, or it's going to go of this form, which then of course means we know what y prime and y double prime are. So when you differentiate, we got to kick the counter up by 1. So we get n times a sub n times x to the n minus 1 for the derivative. And then the second derivative is going to be a sum from 2 to infinity n times n minus 1 times a sub n x to the n minus 2. So pretty much every single one of these problems, you want to start this way. Okay, so now we're going to go ahead and plug those in. So we're going to take these different series, put them in to their respective spots. So we're going to get, if I multiply this by 1 plus 3x, I'm actually going to get two different series. Multiplying by 1 gives me the one that's written there. Multiplying by 3x, that's going to give me 3 times this stuff. And then multiplying by x kicks that up to the n minus 1. So there's that one. So those two came from the first bit. Then I'm going to take y prime and multiply it by x. Okay, so that's going to give me the sum from 1 of n a sub n x to the n. And then I need to add 2 of the original. So that'll be the sum from 0 of 2 a sub n x to the n. So again, all I did was I brought that stuff out front and I brought them into the series. Okay, so then the next step is to make it so that all of these x's are raised to the same power. So we need to do some shifting. So like this first one, I want to shift it by 2. The second one, I'm going to want to shift it by 1. And the last two, I don't want to shift at all. They're already x to the n's. So if I shift that first one by 2, that's now going to be a sum that starts at 0. And we're going to have n plus 2 times n plus 1 times a sub n plus 2 times x to the n. So since I shifted by 2, I need to put in n plus 2 everywhere. So it's a horizontal shift. So since I went down 2, I'm actually adding 2 to what I put in my function. Okay, so then the other one, I want to shift it 1. So this is going to be the sum from 1 to infinity. And it's going to be 3 times n plus 1 times n times a sub n plus 1 times x to the n. So that one I put in n plus 1. And then the other two, like I said, I leave those alone. Okay, so now I've got them all as x to the n's. So the next thing I want to do is I want to make sure that all of these counters are starting at the first place or at the same place. And so the way we're going to take care of that is by pulling out the ones that don't match. So basically I'm going to start with the ones with 0. I'm going to put zeros in there. Then they're going to be starting at 1 and I can lump them all together. So this is going to look like then. Okay, well, when I plug in 0 to this first one, I get 2 a sub 2. Because I also get an x to the 0, which is equal to 1. The other one, when I plug in 0, I get plus 2 a sub 0. And then the rest of them can all be lumped together. And so I'm going to have this real crazy kind of setup here. I'm going to have n plus 2 times n plus 1 times a sub n plus 2 plus 3n times n plus 1 times a sub n plus 1 plus n plus 2 times a sub n And that n plus 2 a sub n came from adding these two together. And all of that is times x to the n. So we're pretty close. What we do now is we set up our recursion. So we know that this has to equal 0. Remember, that was the whole point. It's going to equal 0. So here's what I know. I know that 2a2 plus 2a naught has to equal 0. Because this stuff, that's the only constant piece. So that's going to have to equal 0. So this actually tells me that a2 is equal to the negative of a naught. So I've got that. The other thing I know comes from all this stuff in the bracket. So I'll go ahead and just rewrite this. I'm going to have n plus 2 times n plus 1 times a sub n plus 2 plus 3n times n plus 1 times a sub n plus 1 plus n plus 2 times a sub n. That's also going to equal 0. All right, well, there's our recursion relationship. Basically, if we know any two terms, I know the one after it. So here's how this is going to go. A naught, we already know that that's a free choice, so it'll just be A naught. A1, also a free choice. There's always going to be two free choices since this is a second order. Now A2, we already know that that's equal to negative A naught. So now let's get A3. Well, to get A3, I'm going to come over here, and I'm going to use this recursion relationship, but I'm going to plug in n equal 1. So that gives me 3 times 2, which is 6, a sub 3. I get another 3 times 2, which is 6, a sub 2. And then I get 3 a sub 1s. So I can solve this for A3. A3 is going to equal negative A2 minus 1/2 A1. But I also know that A2 is actually equal to negative A naught. So I'm going to plug that back in. So the negative negative turns positive. And so here's A3. It's A naught minus 1/2 A1. Okay, so then you'd find A4. Same thing, you plug in n equal 2 to this recursion relationship. For A5, you plug in 3. A6, you plug in 4, and so on down the line. But let me show you what you do with these then to find our solutions. Okay, so we've got these A's. So this is what I know then about my solution. My solution is going to be y equals A naught plus A1x plus A2x squared plus A3x cubed plus dot, dot, dot. So now let's put those in. So I've got A naught plus A1x minus A naught x squared plus A naught minus 1/2 A1 x cubed plus dot, dot, dot. And then I can separate this into the pieces that have A naught and those that have A1. So I'm going to have y is equal to A naught times 1 minus x squared plus x cubed plus dot, dot, dot. So this was your A naught times 1 a naught times x squared, a naught times x cubed, and plus a 1 times x minus 1/2 x cubed plus dot, dot, dot. And so whatever those other ones are, Mikey, like when you get your A4, your A5, A6, if they've got both pieces, they have both an A naught and an A1, just split them into the 2 chunks and put the A naught bit with the first one and the A1 bit with the second one. Okay, so, and then at this point, you want to find your initial conditions. This is where you could use that, like, for example, I think it said y of 0 was equal to 2. Let me just go double check real quick. Yeah, y of 0 is equal to 2 and y prime of 0 is equal to -3. So if we plug 0 in for x, all of this is gone. And all of that is gone. And we're left with just a naught. So a naught is equal to 2. And then when it comes to the derivative, everything's going to go away except for the a1. And so in this case, a1 is going to equal to -3.
Cool. Thanks, Bruce. I appreciate that.
So you know where to go, obviously, to find 4, 5, 6, and 7. It's just use that same deal.
Yeah.
Okay, cool. Well, let's go take a look at the other one that Thea asked. Is it number 41, I think you said? Yeah, number 41. Okay, so number 41, it's the same idea. I'm going to go ahead and share my screen real fast. Okay, so again, we want to go ahead and find the coefficients, the first 7 in this series. And we've got initial conditions again. We've got y of 0 equals 2 and y prime of 0 equals 3. So that means we want to center it at 0. And they even tell you that above, right, where it says take x naught to be the point where the initial conditions are imposed. So exact same idea. So we got y double prime plus 1 plus 2x plus x squared times y prime, and then plus 2y equals 0. All right, so I'm going to stop sharing. We'll go back to the board. All right, well, we're going to start exactly the same way. So I'm going to help us out a little bit. Since it's always the same form, let's just jump to what this is going to look like. So we're going to have the sum from 2 to infinity of n times n minus 1 times x to the n minus a sub n times x to the n minus 2. That was the y double prime. The y prime, we're going to get 3 pieces. So they're all going to start at 1. So we're going to get 1 to infinity, n times a sub n x to the n minus 1, plus the sum from 1 to infinity of 2, n times a sub n x to the n, plus, and then the other one, when we multiply by x squared, we're going to get 1 to infinity, n a sub n x to the n plus 1. So there are those 3 pieces. And then, of course, we're going to get plus 2y. So that's going to be the sum from 0 to infinity of 2 a sub n x to the n. Okay, so there are the 5 sums. But we're going to do exactly what we did before, which is start by getting them so that they're all x to the n. So you'll notice that these 2, they're already x to the n, so we don't have to do anything with them. But the other 3 we have to shift. So the first one we got to shift by 2 again. So that'll be the sum from 0 to infinity of n plus 2 times n plus 1 times a sub n plus 2 times x to the n. The second one, we have to shift it by 1. So that will also be from 0 to infinity. This time it'll be n plus 1 times a sub n plus 1 times x to the n. I'm not going to bother rewriting these two because they're going to be what they are. But then this other one, we need to shift it by 1, but we need to shift it by 1 the other way. So now, instead of starting at 0, shifting it down, we're going to shift it up. So there's plus a couple more sums. But then this one's going to be the sum from 2 to infinity of n minus 1 times a sub n minus 1 times x to the n. So those two sigmas are the two that we didn't have to shift. So the only difference with this one is that since we were shifting the other way, we're now putting in n minus 1, and this counter goes up. All right, so we're going to start pulling stuff out. And for this one, since the highest n is n equal 2, right, these other ones were still n equal 1 and n equal 0. Well, we'll just start with 0, pull that stuff out. And then we'll plug in 1, pull that stuff out. And then from there on, it will all get lumped together. So let's see what these look like. So plugging in 0, I'm going to get 2a sub 2 from this guy. And crap, I just erased what those were. Shit. What was that last one? Was that just a regular? Oh, it's multiplied by 2. Okay, so that'll be plus 2a sub naught equals 0. So that was the n equal 1 case, or n equals 0 case. So then we go to n equal 1. Okay, well that's going to give us 6a sub 3 plus, oh shoot, I forgot one in here. When I plug 0 in here, I get a sub 1. So I think for the 0 case, it should be 2a2 plus 1a1 plus 2a naught. Okay, so then when we go to 1, we're going to get 6a3 plus 2a2. And then we have to go to this one. Was that a 2 times n minus 1? Or no, 2 times n?
Yeah.
2 times n. So it should be 2a sub 1. And then this guy is going to be plus 2a sub 1. I believe I erased those. So I'm trying to go off memory, I think. So please double check that. So then the next one, well, now we're at 2 and forever. And so now we can combine these things. So the other recursion relationship is going to look like n plus 2 times n plus 1 times a sub n plus 2 plus n plus 1 times a sub n plus 1 plus, and I think it was n times a sub n, I'm going to go with it, plus n minus 1 times a sub n minus 1 plus 2. Right? And all of that has to equal 0. Okay, so just like with Mikey's, I'll give you the first few, and then I'll leave it for you guys to kind of finish it off. So A0 is its free choice, as is A1. But then A2, we're going to come up here. We know that A2 is equal to, if I solve this is A2 is minus A0 minus 1/2 A1. So I'll put that in here. So A3, I'm going to get from this one. So A3, it's going to be minus 2/3 A1 minus 1/3 A2. But I'm going to plug in for my A2. So it's minus 2/3 A1 minus 1/3 times minus A0 minus 1/2 A1. So it's going to be minus 2/3 plus 1/6, which I think is minus 1/2. So we get 1/3 A0 minus 1/2 A1, I think. And for this one, I'm going to go one more for you, because to get this next one, we have to use the recursion relationship that we just built. So to get A4, I'm going to plug in n equals 2. So that's going to give me 4 times 3, which is 12A4 plus 3A3 plus 2A2 plus 1A1 plus 2. Hold on. That should be 2A sub n, right? So that should be 2A sub 2. All right, but I know A2 and I know A3. So let's put those in. So we get 12A sub 4 plus 3 times 1/3 A0 minus 1/2 A1 plus 4 times A2. So 4 times minus A0 minus 1/2 A1 plus 2A0. So that has to equal 0. So let's see what this does for us. I'm going to get 1A0 minus 4 plus 2, which I think is a minus 1A0. I get minus 3/2 minus 4/2 is minus 7/2 A1. So it looks to me that A4 is 1/12 A0 plus 7/24 A1, I think. But I am terribly unconfident in all of this because of the fact that I erased that step once upon a time. Okay, well, crossing my fingers that we're good. But anyway, so there's your A4. All right, A5, plug in n equal 3. A6, plug in n equal 4, and so on. It is possible to simplify this recursion relationship a little bit, but I'm not going to bother with that because this is as far as I'm taking you.
Cool. Thank you, Bruce.
All right, you're welcome. So, yeah, they get ugly. The algebra is what it is. But now we're at least able to start constructing these functions, which means in an applied situation, if what we're looking for is a function that's a solution to some differential equation, we can at least go as many terms as we need so that we're close enough, depending upon what that close enough is. All right, so take it for what it is. It's a way to find solutions by basically just saying, hey, we don't know what the function is, but all right, let's just build it. And so that's what we're doing. We're actually constructing the solution. We're constructing it piece by piece. So. All right, good?
Yep, thank you.
You are welcome. All right, so now you kind of see how we deal with being at an ordinary point. We just go with, hey, let's create a series and let's do this. But we do need to talk a little bit about singular points, because this trick won't really work for singular points. Because singular points, there's an issue there with the fact that it makes all, remember, singular means all those polynomials are all equal to, or that the first function is equal to 0 when all the rest of them aren't, right? And that leads to a problem. So we need to talk a little bit about those. So let's remind ourselves about what that means again, ordinary versus singular, and we'll start classifying singular points. And then we'll look at some of the things that we can do when we have to attack problems at singular points. So again, singular versus regular, or sorry, ordinary. All right, so here was kind of the deal. We had P of X times Y double prime plus Q of X times Y prime plus R of X times Y. And what we saw was that for it to be ordinary, P of X naught does not equal 0. So we say that X naught is ordinary in this case, right? And then singular is where this does equal to 0. Now, this is not quite complete because we need to make sure that Q and R are also not both 0. So because we're talking proofs and stuff, I'll be good here. But I'm just going to put here in Q of X naught and R of X naught are not both 0. Okay, so we call those singular points. Now, in terms of how we treat singular points, it depends what kind they are, because there are actually different kinds of singular points. And so every singular point can be classified as either regular or irregular. Okay? So if we can rewrite it, so if we can take that differential equation and rewrite it, x minus x naught squared times some new function a of x plus x minus x naught times some new function b plus c of x times y. Okay, so if we can rewrite it like this, then we say that x naught is regular. Okay. Otherwise, it is irregular. So I know that this is kind of convoluted, but basically what we're looking for is that problem spot more of a problem with the derivative? Like, is that 0 have a greater multiplicity? So notice that the multiplicity of x naught here is 2. For the other one, it's 1. And so when we're in that situation, then this is going to be called a regular singular point as opposed to an irregular. So let me show you how this plays out. I'm going to give you a differential equation that has multiple singular points. And we're going to look and see which ones are regular and which ones are irregular. All right, so here's the example. So let's go with this one. We've got 2x times x minus 2 squared times y double prime plus 3xy prime plus x minus 2 times y, that equals 0. So let's start by just listing out singular points. So singular points are going to be x values that make the multiplier on y double prime equal 0, that don't make all the rest of them equal 0. So if you just look at this, and I were to ask you, tell me x's that are a problem or that make it 0, you'd say, okay, well, one of them would be 0, and the other one's going to be 2. Now, just because they make this 0 does not mean that they are singular points. We need to make sure that they don't make everything 0. So if you were to plug 0 in, P is 0, Q is 0, but R is not. R is going to be -2. So 0 is a singular point. Similarly, if we plug in 2, P and R, those are both 0, but Q is not. So that is also a singular point. All right, so then the question is, regular or irregular? Okay, so remember what we're looking for is we want to be able to write it in these form. So let's actually start with 2, because I think 2 is a little bit easier to see. So basically the question is, can we rewrite this as x minus 2 squared times something plus x minus 2 times something else times y prime, and so on. So you definitely see the x minus 2 squared. So a of x would be 2x. All right, cool. Can we rewrite this one as x minus 2 times something? And the answer to that is no. Because if we try to put in an x minus 2, it would be 3x minus 6, which would require a plus 6. And now we're adding something, and that's a problem. So x naught equals 2, this is actually irregular. Okay, so what about x equals 0? So for that one, we need to be able to write this as x squared times something. All right, so right now you don't see an x squared, right? You got just plain old x. So here's what we're going to do. Let's just multiply everything by x. Since it's an equation, I know I can do that. So check out what this looks like now. So now we've got 2x squared times x minus 2 squared times y double prime plus 3x squared times y prime plus x times x minus 2 times y. Okay, so now we see that a would be 2 times x minus 2 squared. That's the bit that's being multiplied by x squared. Similarly, you can see over here that c is x times x minus 2. You don't really have to worry about that last term, the thing times y. We don't really care about that. But now the question is, can we write this middle term as x times something else? And the answer to that is absolutely. In this case, b is equal to 3x. Right? X minus 0 is x. X times 3x is 3x squared. So it is possible to write our original differential equation in this form. And so that would tell me that 0 here is regular. So that's really the check. We look and see whether or not this is regular or irregular. All right, but I know that that's kind of a pain, right? You look at that and you go, ugh, trying to do the algebra, get it so that it's in the right form. It's extremely difficult. I don't know if I'm going to be able to do it, blah, blah, blah. Well, it turns out that there's another way that you can check for regular or irregular just by taking a limit. Okay, so let me show you how that works, because this is usually a little bit easier for us to see regular versus irregular. All right, so here's what we're going to do. We're going to take a limit. We're actually going to take a limit, and this is going to tell us whether or not these guys are regular or irregular. So I'm going to leave this up for a second. So let me show you what we're going to do. So really the kicker here, right, if you think about this dividing out kind of business, or writing it as the x minus x naught squared versus x minus x naught, is think about dividing it. So if you were to divide out, then one of those is going to cancel, right? If we look at like the p over the q. And so that's what we actually want to look at to see whether or not it's regular or irregular. So here's the process. We're going to look at this limit first. Okay, so again, generically, we've got P, Q, and R. Right? And so basically, if we were to kind of divide out, what we would see is Q over P, right? And R over P. But here's what we want. We want to actually look at the limit as x goes to infinity of x times Q over P. And we want to look at the limit as x goes to infinity of x squared times R over P. And basically, what we need here is for those limits to be finite. If these are finite, then it's a regular. So it'll be a regular singular point. So to be quite honest, that's how I check to see if it's regular. Now I chose just X. That's for if we're at 0. If we want to be really good about it, we would have an X minus X naught. And in this case, an X minus X naught squared. And I think this will be a little bit easier for you to see why these ended up being regular versus irregular. All right, so let me show you. Let's go back to this and actually run these limits. Okay, so if we start with the 0, for the 0, we're going to legit have the limit as x goes to infinity of x times 3x, that was our q, divided by 2x times x minus 2 squared. And then the other one that we need to look at is the limit as x goes to infinity of x squared times x minus 2 divided by 2x times x minus 2 squared. So the x minus 2, that was our q, or sorry, our r. The p is on the bottom. We have x squared. Okay, so take those limits. So notice that these are polynomials, right? They're rational functions. So we get an x squared over an x cubed. So that limit is 0. This one, we have x cubed over x cubed, which means we just need to get their coefficients. It'll be 1x cubed over a 2x cubed on the bottom. That guy is 2. They're both finite. Tells me 0 is regular. Okay, so then if we look at the other one, you'll see where we run into a problem. We're going to have the limit as x goes to infinity of x minus 2 times 3x over 2x times x minus 2 squared. And the other one, limit as x goes to infinity of x minus 2 squared times x minus 2 over 2x times x minus 2 cubed. Or not cubed, sorry, squared. All right. I gotta apologize. These limits, they're not supposed to go to infinity. They're supposed to go to those singular points. Sorry about that. And this legit changes everything. I'm so sorry. Because if you go to infinity, they always work. All right, So this, of course, is going to require L'Hopital's rule sometimes. But let's come back to this guy. One of the x's cancels. So the other one we can plug in, we get 0 over something, which is 0. For this other one, just cancel some stuff out, we get x over 2 times x minus 2, which is going to be 0 again. So both finite, it's regular. Now for this one, check out what happens. Just look at the first one. X's cancel. One of the x minus 2's cancels. So we're looking at the limit as x goes to 2 of 3 over 2 times x minus 2. You can see right away that that's infinite, which tells me irregular. So this is the fast check. You take your limit as you go towards those points of these ratios. Anyway, as long as you don't botch it like I did at the start, it's pretty fast. And we'll let you know what you've got. Okay, so this is how we classify singular points as either regular or irregular. Okay, so how you solve things at the different singularities depends on whether they're regular or irregular. We're not going to really go into that. That will be, you'll see that in some future class that you take. But what I wanted to show you is a specific kind of differential equation that occurs at a regular singular point. And those are what we call Euler equations. All right, so Euler equations always have the same form. And their form looks like this. We have a x squared times y double prime plus bx times y prime plus c times y equals 0. Okay, so notice that there is a singular point. There is a singular point at 0. So then notice that it's regular because of the fact that it's x squared times something, x times something else. So it's singular and regular. Okay, so what I'd love to be able to do is do some sort of a power series, but the problem is I can't center it at 0. There's definitely an issue there, right? X equals 0 is a problem because then if x is equal to 0, this term's gone, the second term's gone, and what we're left with is only the trivial solution of y equals 0. So that would make Wes really happy, but we want to find non-trivial solutions as well. All right, so the way we're going to do this is the same way we've always done this, which is make a guess. Let's think about what kind of a function might actually work here. So anybody see a good type of function that might work in terms of being a solution to these?
Some form of polynomial?
All right, I definitely like that idea, right? Think about if it's a polynomial, then every time we differentiate, we go down 1 degree, and we're multiplying by another x, which brings us back up to that same degree. So I think that sounds great. So let's go with that. And let's just say, let's make a guess of y equals x to the r. because why not? You make guesses all the time in differential equations. All right, well, if y is x to the r, then y prime is r times x to the r minus 1. Y double prime is r times r minus 1 times x to the r minus 2. And so if we put those in, we're going to get a times r minus 1 times x to the r plus b times r times x to the r plus c times x to the r. So all of those have an x to the r, so I'll factor that out. So if it has a form of x to the r, then it's going to have to look like this in terms of its solution. So r is going to have to satisfy this equation. So we really have two choices. One is x to the r could equal 0. But I don't want that solution because that basically just tells me x is equal to 0, which was aforementioned a problem, right? So this is a nope. So our only other option is for this, t equals 0. Well, it's a quadratic, and it's going to lead to a couple of solutions. And depending upon what those solutions look like, we'll have our solutions to the Euler equations. So this probably feels kind of similar to what we did before, because it is. It's just we're not guessing a form of e to the r. This is now x to the r. So our variable is no longer in the exponent, it's in the base. Okay, well, same thing's going to happen as always. We could get two real solutions. We could get one repeated solution, or we could get two complex solutions. Okay, well, let's look at those three different cases. So the first case, case 1, is going to be two distinct real. Okay, so we'll call them R1 and R2. Then our solution is just going to be C1 times x to the R1 plus C2 x to the R2. So super easy. It's just whatever those R values are, the two different R values go as our powers of x. So this is where you can start seeing that the power series won't really work out very well. What if those are negative? Right? We have no, well, we do have ways of trying to turn things that have negative powers into power series, but they're kind of a pain. And for sure, we can't center it at 0 anyway. Okay, so you're starting to see why there might be an issue. But that's case number 1. Awesome, two distinct real. So case number 2, this of course is, how about one repeated real number? Okay, so we know then that we're going to have that C1 x to the r, but we're going to have to do something to this other one. We can't just use x to the r again. So we need a fundamental set. So what did we do before?
We just multiplied by by x.
Okay, so before we just multiplied it by x.
Yeah.
All right, so what if we did that here?
It would change it to x to the r plus 1.
Okay, so that would give us x to the r plus 1, which would be a second real number, which is not what we had. So that kind of sucks. We can't just multiply it by x. But what we can do is reduction of order. say, okay, I need to multiply it by something. Let me call that something u. And then go through the process. Take u times x to the r, take its derivative, its second derivative, plug it in, yada, yada, yada. I'm just going to jump to it because I don't think any of us really want to go through that. But it turns out that this time, what we multiply by is the natural log of x. So if you get repeated roots, you're just going to take x to the r times the natural log of x. All right, so there's case number 2. So then lastly, we go to case number 3, which is going to be the, what if we get complex roots? Well, what you would do if you had your complex roots is you would go ahead and put them in. So we would get, say, x to the a plus bi, and then x to the a minus bi. But of course, we don't really want that. We want those complex. But what we can do is make use of Euler's formula. And you may remember from when we did this before, when we ran into complex roots, we know that x to the, or e to a complex number can be written as sine and cosine. So here's what we do. I'm just going to do it for the first one. We're going to get x to the a times x to the bi. Don't worry about the c1 and all that. We can put that back in. Okay, well, I don't want x to the bi. I want e to the something. Well, I know that x is equal to e to the natural log of x raised to the bi. So this is x to the a times e to the natural log of x times b times I. And now I can make use of Euler's formula. And so what we end up getting when we have the two complex roots, we're going to get y is equal to c1 times x to the a cosine of b natural log of x plus c2 times x to the a sine of b natural log of x. So just like in the one repeated root, we get that natural log of x shows up. It shows up in here too. And it really shows up just because we're trying to make use of Euler's formula. And we need to change it from being base x to being base e. Okay, so there's your third case. So depending upon what we get, either 2 real, 1 repeated real, or 2 complex, we know exactly what the form is for solutions to these kinds of differential equations. But again, these are special, right? They're a special class. That's why they're even named, but it's just a matter of finding those. So let me show you a couple of examples because they're not that hard. It's just a matter of doing it. All right, so here you go. Let's take this one. Let's look at x squared y double prime plus 5xy prime plus 4y equals 0. So again, x can't equal 0, so we're going to be on one side of it. And in most real life situations, we're on the positive side, because usually our independent variable is a positive number. All right, well, let's build our polynomial. Now, this one we got to be a little bit more careful, because this polynomial, it's not as easy to write as what we did before. Because what we're going to get, the general form is a times r minus 1 plus b times r plus c. Okay, so the last two are pretty easy. It's going to be what you're used to. So this one's going to be 5r plus 4. But this one, we're going to get 1 times r minus 1. So just make sure you throw on that r minus 1 instead of just the r. Okay, so if we distribute, we're going to get r squared plus 4r plus 4, which is r plus 2 squared. So we're in the repeated root case. Well, we know exactly what to do then. Y is going to equal C1 times x to the minus 2. That was our first. And then the second one is going to be x to the minus 2 times natural log of x. And there you go. There's your fundamental set. Obviously, if this was a non-homogeneous and now equal to something else, well, now that we got that fundamental set, we know where to go, we know what to do, right? And we can go from there. All right, so what do you guys think? Do you need another example?
Pretty simple.
Yeah, I don't think you really do. Just make sure you always do that r times r minus 1. Let's do one more. We'll do one more.
I mean, you could simplify that polynomial even further down, where it's like ar squared minus, plus b minus ar plus c.
Yes.
That way you don't have to, like, sort of just less work to do, I guess.
I don't know if it's less work. It's just doing it in a different place.
Yeah.
But you are right that if we were to distribute that out, you would get ar squared plus b minus a times r plus c. And now the first and the last don't change. It's the middle one that changes. And that's fine. If you want to see it that way, that works too. So let's do one more, just for the hell of it. So let's say we've got x squared y double prime plus xy prime plus y equals 0. And so maybe, hey, let's use this form that Theo was just talking about. So the first and third are exactly what we think. We're going to get r squared plus 1. And then the middle term, I have to do b minus a. So 1 minus 1 is 0r. So that one turns out to be r squared plus 1 equals 0. So that's going to give us r equals plus or minus I. So we've got complex roots. So our solutions for this one then, we're going to throw in the sines and cosines. But we start with x to the real part. Well, x to the 0 is 1, so that's not going to be there. So we're going to legit just get cosine and sine. And this is going to be the cosine of the natural log of x. And the other one's going to be sine of the natural log of x. If you go back and you look at the derivation, it was b times log of x. But in this case, b is equal to 1. All right, so there you go. All right, so Euler equations, they are what they are. But they're special because they've got a good form, and we've already done all the work. We did the work one time, found the 3 different scenarios, and now we're good to go. All right, well, there are other kinds of equations that lead to singular points. There are other processes, but like I said, I'm not going to show you anymore. We're just going to use this as an example of what you do when you're by a singular point. Because what I'd rather do is move on to the next chapter and talk about Laplace transformations. But I think I'm going to go ahead and call it for today. I know we're a little bit early, but I don't see the point in starting Laplace transforms. No, let me at least introduce them. We won't use them or anything, but let me just show you what they are. Okay, so we're moving to the next chapter. Pretty sure it's chapter 8. But we're going to talk about these things called Laplace transforms. They're named after the French mathematician that kind of came up with it. But the Laplace transform basically just does this. So we're going to use curvy L for the Laplace transform. And we're going to put some function into the Laplace transform. Okay, so that could be anything. It could be t squared. It could be, you know, whatever. Let me make these brackets. It's really like a function. All right, now this is how it's defined. It's an integral from 0 to infinity times e to the negative st times f of t dt. So if you ask me where'd that come from, my answer is going to be Laplace decided that he wanted to look at transforms of this type. Okay, so this is just how we define it. In terms of what it's good for, well, you'll see. You'll see why we care about these in a little bit. But let's just start by looking at a few. Let's actually just do a couple so you can get the feel for how these work. All right, so for example, let's find the Laplace transform of just a constant function. Okay, so 4, negative pi, you know, whatever. So a constant function. So this is going to be the integral from 0 to infinity, e to the minus st times that constant, dt. So that constant will come out front, and then e to the minus st, we integrate that, we're going to get minus e to the minus st over s, evaluated at 0 and infinity. All right. Do you remember what to do with infinite bounds? Do you remember how those things work?
Not really.
Okay, yeah, I'm hearing lots of crickets. So when you have these are called improper integrals. And technically what we have to do is take a limit. We call this, say, b. And we say, what's the limit as b goes to infinity? I like to just go ahead and jump in and plug in the infinity. But what this would do for us then, we plug in infinity, we're going to get minus 1 over s e to the s times infinity plus 1 over s. So what's going to happen to this piece?
Isn't that E just going to drop? Well, isn't that whole term just going to go to 0?
Yeah, we end up dividing by a really large number. So this basically goes to 0. And so what we're left with is just C over S. So there you go. You've now transformed, you found the Laplace transform, any constant. If it's 1, 1 over S. 4, 4 over S. -6, -6 over S. So these Laplace transforms are always going to be functions of S. Okay, because S is sort of the little dummy variable, but they're always going to be functions of S. All right, now we did make an assumption here, and it was one that I don't know if anybody caught, but when we say this, when we say the Laplace transform of C is equal to C over S, we do need to state that this is only true if S is greater than 0. And that came into play with this step where we said, hey, as we plug in infinity, this goes to 0. Because if S were negative, that would have brought this back to the top, and then it would have gone to infinity, and therefore we wouldn't have a convergent integral, and it wouldn't be the actual value. Okay, but there's your Laplace transform for a constant. Kind of whatever, right? Big deal. So let's do one that's a little more complicated. Let's do an exponential. So this time, let's do a Laplace transform of E. And we'll do it generically. Let's just do E to the AT. So we're going to have the integral from 0 to infinity, e to the minus st times e to the at dt. That's the integral from 0 to infinity of e to the a minus s times t. So now let's integrate that. So that's going to give us 1 over a minus s times e to the minus, or sorry, a minus s times t that we're now going to evaluate at 0 and infinity. So the 1 over a minus s, let's just go ahead and pull that out. And let's talk about this thing in terms of what we need for it to converge, what we need to get a finite value. So obviously the 0 is not a problem. I plug in 0 for t, no big deal. I get e to the 0, which is 1, life is good. It's the infinity that I definitely need to worry about. So what can you tell me about this that's going to make it so that when we put in infinity for t, that drops to 0?
If a minus s is, well, if the a minus s chunk is negative, essentially, that's going to allow it to.
There you go. Yeah, so
converge.
for this to converge, I need a minus s to be negative. So I need a minus s to be less than 0, right? Or s has to be bigger than a. Okay, well, if we go with that, then look at what happens. We get 1 over a minus s times 0 minus 1, because the first bit's going to go to 0, and the second one I'm going to get e to the 0, which is 1. So distributing that minus sign, I get that the Laplace transform of e to the at is 1 over s minus a. I just switched them because I'm multiplying that minus sign. Okay, well, we just found the Laplace transform for any exponential function. Boom, we're done. So you could do this for anything. You want to find the Laplace transform of cosine? Okay, take cosine times e to the minus st and integrate. You want to find the Laplace transform of natural log? Okay, put natural log in here. So natural log times e to the minus st, integrate. You want a polynomial? Put in, t to the fourth. Okay, integrate e to the minus st times t to the fourth. So this is the Laplace transform. It's actually really easy to do. Well, it's super easy to set up. May not be super easy to do because it often leads to integration by parts. But there it is. All right, but I think this is where I am going to stop. So what we'll do next time is we'll look more at the Laplace transform and some of the theory behind it, and then we'll start seeing why it might be useful for, well, I don't know, solving differential equations. Okay,